Hello everyone, I am Haruna Umar Adoga. In this video, we are going to be looking at using the LogicWorks simulation software. This is part of a series of videos that would attempt to explain and demonstrate how the LogicWorks simulation software works for the design of basic electronics logic circuits. LogicWorks is a software used for designing electronics logic circuits. It's basically used by electronics engineers, computer scientists, students, and instructors to accomplish the goal of logic gates and electronics circuit simulations. So this document, I have listed out some of the truth tables, the basic truth tables that we are going to work with, and we're going to start with the basic AND gate, OR gate and the truth table, NAND gate and the truth table, exclusive OR, then proceed to draw more complex. This really not that complex anyway, but for the basics, we'll try to see if we can achieve this in this video, and this is part 1 in the series. So in subsequent videos, we'll attempt to explore more. So now let's go to the LogicWorks simulation software. I have installed it on my PC and pinned it to taskbar. This is the icon. So the copy I have is LogicWorks 5. You can install any copy 4, 3. So you get a copy installed. Now when you launch, you have this welcome interface that prompts you to either create a new circuit, or if you choose to create from here, that's fine. But if you close, you can always create a new circuit here. If you choose new, it's going to ask you if you want to create a circuit, text document, device symbol, or model wizard. What we want to create here is a circuit, so I'm choosing circuit. Okay, so this is the interface. This is where we're going to do our design. That's the basic interface that we're going to do our design. These icons you see here, I'll get to explain some as we use them. That's in subsequent videos, and even in this first video, if there's any need for us to use any, I will let you know what it's there for. That's what the particular icon we are using, how it's being used, and when you should use it, the tools that are presented with this icon. So looking around, let's just have a brief walk around. If you look up here, you can see we have all libraries. This part, this is where you choose the library of the tools to use. That's either you want to use the simulation gates. Simulation gates will give you logic gates like AND gates. AND 2 here simply means AND with 2 inputs. If you click on it, you can see it's showing there, it's displaying. AND 3, just AND gate with 3 inputs, and 4, like that. So the library, it means if you want to use a logic gate, you have to go to the simulation gate library. If you want to use simulation IO here, simulation input output, That's for like input to the logic gate or output. The input and output here, they are being referred to as binary probe is for the output. That's like the display for binary. There is also a display for hexadecimal values, but that's not gonna be covered here in this first video. Then binary switch, that's for binary input. Mind you, we have a whole lot of tools here, a whole lot of items here, but like I said earlier, we are going to focus on using the basic ones just to design our simple circuit. So let's just get straight to it. What we have here, I just showed you the binary probe, the binary switch. The NOT gate is in simulation IO, since it's also a logic gate, simulation gates. So if you go to simulation gates, scroll down, you can see NOT. Also, you can filter from here, just a search. Maybe I can just filter NAND, and you can see the list. Here we have all the NAND gates that are available. Now let's start by showing how all this works. Let's use a probe, a simple probe, simulation IO. In simulation IO, if you pick a binary probe, that's a like display binary probe, and a binary switch. Let's start. So it's the normal drag and drop you're used to. So we can connect this to that. This just input output. So for the binary switch, now the input is at 0. You can see that the display is 0. If you change the input to 1, the display is 1. You could also flip this vertical, horizontal, just any location you want. Flip, rotate, you can do all this. So I'm just trying to show you how you can rotate it if you don't like the positioning. So for the NOT gate, and as we all know, the NOT gate is used as a negation or an inverter. It's used to invert the binary input, and that's if it receives 0, it gives 1 as the output, and if it receives 1, it gives 0 as the output. So let's see how this works. Now, some of the tools here, this icon here is the delete button. That's zap, it's clearly written here, zap. So if you click on it, you can delete the connections in between, and you get back to your pointer. Let's use the NOT gate. You go to simulation gates and scroll down. You have your NOT gate. You just drag and drop. So introducing a NOT gate to this design gives the opposite value. That's if the input is 1, we should have 0 as the output. If the input is 0, we should have 1 at the output. Let me magnify this view, just so you can have a better view of what's really going on. Okay, now we can connect these. You just drag and connect. So you can see that the input is in 1, and the output, because of the NOT gate we are using here, the input is in 1, but the output is displaying 0. Input 0, output is 1. So let's proceed please with using, so the AND gate, we have the AND gate here. We can pick that from simulation gate and with 2 inputs. Let me keep the 2 windows side by side so we can work with. Okay, we can pick the AND gate from this. That's from library. You choose simulation gates and select AND. It depends on the number of inputs you want. AND with 2 inputs. We've selected it already. Okay, let's see. I'm trying to pick. All you need to do is drag and drop. Let's see, drag, drop. Okay, so now we need to have a display unit for this. That's like the output, and we get that from simulation IO, input output. And if you already have the display unit here or the input, you can just copy. It's either you copy, paste, or you can duplicate. If I choose to duplicate, it means anywhere you click, it's going to drop a copy of. So we don't need this and this. So for this binary switch, that's for the input, we can also duplicate. Let's duplicate the 2 inputs. So you can connect that. Connect. So for the AND gate, let me clear this so we can fill the inputs based on what we have here. For the AND gate, you realize that we have 2 inputs, A, B. We can use this text, this tool to write, just to make it more clear. We have A and B as inputs. So A, B as inputs. If A is 0 and B is 0, you can see the output is 0. If A is 0, B is 1, you can see the output is 0. So it simply means if A is 1, B is 0, the output still will be 0. So if A is 1, B is 1, the output is 1. The output is 1. So for the OR truth table, we can pick that from here. That we pick the OR simulation gate, OR with 2 inputs. You can scroll down, OR with 2 inputs, drop. So we can just duplicate the output, and same thing with this, duplicate. Yeah, I think we can delete this now. Okay, and we can just connect this. So for the OR truth table, let's fill this. Let's fill the table. Let's fill this table. 0, 0, that's if A, the first input is at 0 and 0, you can see that the output is 0. And if the second input, that's the second entry here, if we have A as 0 and B as 1, that's for OR, you can see that the output is 1, and if you have A as 1, B as 0, the output is 1, and if you have 1 1, the output is 1. You can actually do this without using LogicWorks, but this like the basics, so I don't want to skip this. That's why I'm starting from this. Eventually we're going to get into more complex circuit designs using hex inputs, hex outputs, multiplexers and all that, but it's really cool if we start from this. So let's scroll down. The NAND gate, you can also pick that from here. That library, don't forget you have to choose simulation gate. Then NAND, you can just type NAND with 2 inputs, pick, and you can duplicate this. Let's just drop this and duplicate. It's either you copy, cut, or duplicate. It totally depends on what you want to achieve. So for the NAND gate here, it's just a negation of the AND gate. So you could even have this by using an AND gate with a NOT gate attached to the output. That's before you have the output, you have a NOT gate. So using this NAND gate, we can just fill the table. When A is 0, B is 0, we have the output as 1. When A is 0 and B is 1, the output is 1. When A is 0, B is 1, that's like same thing, output is 1. When all the outputs are high, that's 1 1, the output is 0. So for exclusive OR, you can just get that from here too. XOR, it depends on the number of inputs, 4 inputs, 8 inputs, or 2 inputs. What we have here are 2 inputs, so you can just pick from what we've shown so far, from what I have demonstrated here. You can just pick and do the same thing. So now let's scroll down to what we have. So I have a truth table here that will take 3 inputs. That's 3 inputs will give you 2 raised to the power of n. For n inputs, you have 2 raised to the power of n, where n is the number of inputs, number of variables used as inputs, and 2 raised to the power of n number of possible combinations. So for this, we'll have 8 possible combinations. That's, if you count from here, we have 1, 2, 3, 4, 5, 6, 7, 8. That's from 0, 1, 2, 3, 4, 5, 6, 7. This actually counting in binary. This 0, 1, 2, 3, 4, 5, 6, 7. So what we'll do now is to design this. This part is actually like an introduction to De Morgan's theorem. You get to see how De Morgan's theorem works in my subsequent videos. So let's draw this first circuit using this equation. This output X is equal to A plus B plus C complement. Some call it complement, some call it prime, but the idea is like a negation, like an inverter. It's not directly the value of A or B. The addition, the sign plus here is OR, logical OR. So A or B or C with an inverter, like on everything on the output. If you look at B, the second equation, A equals A prime or A complement and B complement and C complement. You can see that this complement is on each input, so it's also represented here from this diagram I have designed here. Unlike this that's on the output, on the output, that's on all the inputs, but this is implemented on each of the inputs and also the third one. So let's do this first one and try to see how we can fill in the truth table. So let's clear all this. You can just delete, zap, delete, delete. Delete all this. Okay. So now what we need to do, so to do this, we'll need our binary probe and our switch. That's binary switch. To get our binary probe and switch, we'll go to simulation IO, binary probe. We have the binary probe. We need our NOT gate. NOT gates, you get that from simulation gates. Scroll down to NOT gate, and we need this OR from this equation you can see, and from the gate here, this OR, logical OR. So we'll get that from simulation gates and OR with 3 inputs. So that's what I was trying to explain. It depends on the number of inputs you want. OR 3 here means the OR gate with 3 inputs. You can actually just connect directly, but if you need space, then you can use like a wire. You can drag and connect. So now we need a switch. So go to simulation IO, binary switch. Okay, we've selected binary switch. Drag, drop. We can just duplicate. We need 3 inputs. So here in this case, we need space. You can see you can connect using a wire. Connect. So now we have this. So to fill in our truth table, let's start from here. If A, okay, or we can use our text to specify this equation, to write this equation. This equation is x equals A or B or C prime or complement, depends on how you want to call it. Okay, so this is what we have. So now let's start from the first value. If A is 0, B is 0, and C is 0, this logical OR, so the output, the value of x is 1. If A is 0, B is 0, and C is 1, the value is 0. If B is 1 and A and C are both 0, the value is 0. 1, 1 for B and C, the value is 0, A is 1, B, C, it's still 0. Remember, for logical OR, the value is 1 if only one or both inputs or all inputs are turned on are also 1. So that's the same thing we are seeing here. For A 1, B 0, C 1, that's the same value we have, 0. And this for A, B, all set 1, and for C 0, the output is 0. Then finally, if A, B, C, all the inputs are set 1, the output is 0. So from here you can see that this equation has been designed, that's this the circuit and this the truth table. So looking at the second equation, for you to do this, you can just select the AND gate from simulation gates with 3 inputs, simulation gates and 3, and before each, that's connecting the inputs. After each binary switch, you use the NOT gate on each of the inputs for A, B, and C to connect. Same thing for this. I do believe that this is something you can try on your own. That's based on what we've done so far. You can actually try this. I don't want the video to be unnecessarily long and boring. The idea is for you to know how to design just the basic truth tables and just give it a try to see how you can do this, and you should have the output that's based on the design. You should have the output for this equation for B and C. Subsequent videos will focus on more advanced topics using LogicWorks in carrying out the designs. We'll also look at the full and half adder circuits, De Morgan's theorem, and other logical circuits that we can design. So do not forget to subscribe, like, and share the video if you find it helpful. Thank you for viewing, and see you in another video. Bye.